before the dinosaurs, before anything you'd recognize, this planet had already run through hundreds of millions of years of rulers, catastrophes, and creatures no one talks about. And that is where tonight begins. This is the story of the creatures that came before, the worlds they built, and the catastrophes that erased them, told from the very beginning of life itself. Picture a place with no name yet, because there was no one to name it. 4.5 billion years ago, the thing that would become our planet was barely a planet at all, more a churning ball of melted rock and metal still figuring out how to hold itself together. The ground, if you could call it that, glowed. Rivers of molten stone ran across a surface that had no oceans, no soil, no green, and nothing remotely like the world out your window right now. Overhead, the sky delivered violence on a schedule. Chunks of debris left over from the building of the solar system fell constantly, some the size of boulders and some the size of small countries, each one slamming into the surface and throwing up fresh waves of heat that kept the rock liquid long after it should have cooled. Between the impacts and the radioactivity leaking out of the young rock, this was a world hostile to anything that tried to hold a shape. And yet, every ocean, every forest, and every living thing that has ever existed would eventually trace its origin back to exactly this furnace. So, the question worth sitting with as we begin is a simple one. How does a place this committed to destruction, this relentless in its heat and bombardment, ever become somewhere a living thing could form? But the cooling alone does not explain why life waited as long as it did. Even after the bombardment slowed and the surface hardened, the chemical conditions that life depends on were nowhere close to right. The early atmosphere was mostly carbon dioxide and nitrogen, and the oceans dissolving into it were thick with minerals, but missing the specific molecular arrangements that biological processes require to get started. The temperature had dropped, yes, but temperature was only one variable among dozens, and nearly every other variable was still wrong. Water could sit on the surface without boiling, which was progress. But water carrying the wrong dissolved compounds under a sky that provided no shelter from radiation is not a cradle for anything. The planet had stopped actively destroying its own surface. What it had not done was assemble the particular combination of chemistry, temperature, and shelter that life would need to cross the line from dead matter to something that could persist. So the planet that would one day carry oceans, forests, and every creature that ever drew breath spent its first stretch as something closer to a furnace than a world. The lava cooled. The bombardment slowed. After hundreds of millions of years of being battered by rock falling out of the dark, Earth finally settled into a surface that water could rest on without instantly boiling away. That cooling is the whole answer to why nothing lived here yet. The chemistry that life depends on simply cannot hold together in molten rock or under a constant rain of asteroids. The temperature had to fall first, and it did, slowly, with no one watching and nothing to notice. Once it fell far enough, water could stay liquid instead of flashing to steam, and liquid water is the one thing every chemical step toward life would later need to happen in. The depth of those early seas provided the one thing the surface could not: enough water above to block the radiation pouring through an atmosphere that had no other way to filter it. By around 3.7 billion years ago, The seas were real. The crags stood above them, and the tide moved against the shore in a rhythm that would continue for billions of years before any ear existed to hear it. The world was ready. It was just empty, and it stayed that way, water turning over against bare rock, under a sky no living thing had yet looked up into. If this is the kind of story you want more of, a like helps this channel find the people who'd want to hear it. Back to the story. A cooling planet and an empty ocean are only the starting conditions. What happened next inside that water is the question that changes everything. And the answer is stranger than anything that came before it, because life appeared, and then appeared to do almost nothing for longer than the mind can comfortably hold. Now, imagine the fires have died down, and the seas have spread, and you are standing on a shoreline that is finally calm. The water is warm and shallow in places, stirred by tides and threaded with minerals washed off the bare rock. Nothing swims in it. Nothing crawls along its edge. By every measure you could take, this is still a dead world, a planet of chemistry and weather, and not one heartbeat anywhere on it. Somewhere in that water, though, the most important event in the history of the planet was about to happen. And it would happen so quietly that no eruption marked it, and no fossil cleanly recorded it. Atoms that had only ever obeyed physics began, in some pocket of that ocean, to arrange themselves into something that could copy itself. That is the line between rock and life, and once it was crossed, what came next made almost no sense. Something that could copy itself existed and then appeared to do nearly nothing with that ability for longer than the mind can hold. So why, after such a staggering beginning, did the planet then spend the next billion years looking almost exactly as dead as it had before? But the existence of something that could copy itself turned out not to be the breakthrough it looked like. Those first organisms had no nucleus, no complex internal structure, no way of storing more than the barest minimum of genetic information. They were held in a kind of biological holding pattern by the ocean around them, which was still chemically hostile to anything more demanding. Oxygen was scarce in the water and almost absent from the air above it, and the kind of energy metabolism that complex cells run on requires oxygen in quantities the early Earth simply was not supplying. Every time a slightly more complicated organism tried to form, the environment pushed back. The raw materials were available, the copying machinery existed. But the fuel that would let cells grow larger and do more was still locked away, produced only as a slow trickle of waste by those drifting, dividing specks. What the record shows across this enormous stretch of time is not evolution stalling. It is evolution running at exactly the speed the available chemistry allowed, which happened to be almost imperceptibly slow. The cells were not failing. They were running at the only pace the ocean's chemistry permitted. The strangest part of life's beginning is not that it happened, but how little it seemed to change once it had. Somewhere in that early water, the right ingredients met under the right conditions, and single-celled organisms began to copy themselves. We still cannot say exactly how the first one was assembled. What we can say is what those organisms did once they existed, and the answer is almost nothing visible for an unimaginably long time. They drifted absorbed what they could, released what they didn't need, and divided. That was the entire story for well over 1 billion years. The thing worth holding on to is buried in that long stillness. Some of those cells released oxygen as a waste product, and that waste slowly accumulated in the water and the air with nothing to break it down. No single organism planned this. None of them needed the oxygen themselves at first. They were simply pumping out a gas that would, much later, become the fuel for everything large and fast and hungry. The patience of this stage is the point. Life did not arrive and immediately flourish. It arrived and idled, and the oxygen kept building for hundreds of millions of years before a single living thing on Earth had any use for it. Those idle cells drifting in dark water were quietly building something they had no use for yet. The oxygen those organisms released had been accumulating for hundreds of millions of years without a single creature complex enough to spend it. And when the ocean finally carried enough of it, what followed happened so fast that scientists still argue over how 1 billion years of stillness broke into one of the most crowded moments in the history of life. Hold that long stretch of stillness in your mind, because what breaks it is one of the strangest turns in the whole story of life. For billions of years, the oceans had held nothing but the simplest specks of living matter, drifting and dividing and changing at a pace too slow to see. Then, in a window of geological time that looks vanishingly short against what came before, the seas transformed. Where there had been near emptiness, suddenly there were creatures with hard shells, creatures with legs, creatures with grasping parts and segmented bodies and structures no eye had ever been built to see. The supercontinent of the day, Rodinia, was cracking apart into smaller pieces of land, opening new shallow seas around their edges, and it was in those waters that the change took hold. It arrived fast enough, and from a starting point flat enough, that scientists gave it a name that sounds like a catastrophe. They call it an explosion, though nothing detonated. The puzzle underneath that name is the part that has kept researchers arguing for over a century. Life had sat almost motionless for 1 billion years and more, barely advancing past single cells, held in place by an ocean that did not yet carry enough oxygen to fuel anything more complex. So what changed all at once to turn 1 billion years of near emptiness into an ocean crowded with body plans that have never disappeared? But the change, when researchers look closely at the record, raises a problem that goes beyond simply having enough oxygen in the water. Oxygen levels had been climbing for hundreds of millions of years before the explosion began, and the seas had carried enough of it to support more complex life long before that complexity actually appeared. What the fossil record shows at the Cambrian boundary is a layer of rock almost empty of complex animal life below it and dense with it above, with almost nothing in between to explain the speed of the transition. Transitional forms that should document the gradual accumulation of new body plans are largely absent, leaving a gap that the oxygen story alone cannot bridge. What the evidence points toward is several forces converging at roughly the same moment, each one amplifying the others, shifting ocean chemistry, breaking continents, opening new shallow seas. Early predator pressure creating a sudden incentive to evolve defenses fast. But why those forces aligned so precisely at that particular moment and no other, after billions of years of near stasis, is a question the rock record raises clearly and answers only partially. The explosion happened. Why it happened exactly when it did remains one of the most genuinely unresolved puzzles in the history of life. Then, the oceans filled with shapes that had never existed before, and they filled fast enough that we still call it an explosion. The supercontinent Rodinia had broken into smaller land masses, the largest of them Gondwana, and in the seas around them, complex life arrived in a burst of variety unmatched anywhere else in the planet's record. This is where the long oxygen buildup of the previous stage finally paid out. With enough of it in the water, organisms could grow larger and more demanding. And the leading explanation for the whole event points straight back to those early oxygen makers, multiplying until the seas could support bodies that needed real fuel to run. Almost every basic body plan we still see today traces back to this window. The ancestors of crustaceans, mollusks, starfish, and worms all took form here. Eyes appeared alongside limbs, mouths, shells, and the first hard exoskeletons. Among the new arrivals were the trilobites, armored and segmented, whose shells fossilized so well that they still turn up in rock all over the world. The first fish showed up too, jawless and eel-like, and easy to overlook, except for one detail that changes everything. They carried the first backbones. Every creature with a spine, including the ones that would one day walk on land, descends from those unremarkable swimmers. The explosion was not just more life. It was the moment life committed to the body plans it would keep for the next 500 million years. Filling the ocean with new bodies created an immediate problem those bodies had never faced before. A world full of prey is a world waiting for a predator, and the first one to arrive did not look like anything that had ever existed, built for something the ocean had never produced before. A body designed entirely around finding and killing at a scale that forced everything else to change. By now, the Cambrian seas were crowded. The water held an unfamiliar zoo of small, soft, armored, and spined animals, most of them no bigger than a finger, all of them busy feeding and breeding and bumping into one another in the shallows. In a world this full of small bodies, one rule of nature was about to assert itself for the first time. Wherever prey gathers in numbers, something eventually evolves to eat it. Out of that crowded ocean rose a creature unlike anything that had come before. A swimmer built not to graze or filter, but to hunt. The first animal on Earth, large and equipped enough to sit at the very top of its food chain. Its front appendages extended forward to grasp. Its eyes sat high and swept a wide arc, and its whole body was oriented around finding and closing on prey in a way nothing before it had been built to do. We know it today as Anomalocaris, and even its name carries the bafflement of the scientists who first dug up its scattered parts and could not work out what they belonged to. A single predator, though, raises a bigger question than what it looked like or what it ate. When the very first true hunter appears in a world that has never known one, what does its arrival do to every other living thing forced to share the water with it? But Anomalocaris sat at the top of a food chain that was, by modern standards, almost laughably thin. The animals below it in the water were mostly soft-bodied and slow, without the layered defenses that prey species would eventually develop across hundreds of millions of years of being hunted. A predator shaped by weak competition is not the same as a predator shaped by strong competition, and Anomalocaris, for all its visual sophistication, was working in a world where most of its prey could not fight back, run fast, or hide effectively. Shells were just beginning to appear, burrowing was just beginning to pay off, and the faster swimmers were only starting to earn their speed. The ecosystem Anomalocaris hunted through was still fragile in ways that would take millions of years to fully resolve. And then, around 485 million years ago, something went wrong with the ocean itself. Oxygen levels in the water dropped for reasons still not fully understood, and the extinction event that followed hit the Cambrian's crowded seas with the indifference of a tide going out. Anomalocaris did not survive it. The predator-prey dynamic it had set in motion, still in its first generation, the prey still mostly defenseless, was interrupted before it had properly matured. Once those new bodies were swimming everywhere, the oceans produced their first true hunter, and it ruled them. Anomalocaris, the name means abnormal shrimp, was the top predator of the Cambrian seas, a little over a foot long, which made it a giant in a world where most things were a fraction of that size. It moved by rippling the flexible flaps along its sides, a stable, efficient motion that let it dart and turn without much of a nervous system to coordinate it. The detail that still astonishes researchers is in the eyes. Fossils show roughly 16,000 lenses hacked into each one, about 4 times what a modern fly carries. Which means this animal saw its world in sharp, sweeping detail, long before sharp vision was common anywhere. It likely fed on soft-bodied prey, and one careful reading of its mouth and grasping arms suggests it could seize a shelled animal, rock it back and forth, and work the shell apart at the joints to reach the soft body inside. The point that matters most is what its existence did to everyone else. With a hunter this capable patrolling the water, soft bodies started growing shells, slow animals started burrowing, and the first real armor and the first real speed began appearing in the prey. The evolutionary arms race that would shape every animal afterward began here. With everything in the ocean now forced to change or be eaten, Anomalocaris itself did not outlast the Cambrian. An oxygen crash in the ocean ended it, but the pressure it had applied to everything below it in the water did not disappear with it. A predator ruling the ocean tells only half the story of this period, because the other half was happening somewhere no animal had ever been. The land above those crowded seas was still completely bare, and the question of how life crossed from water onto that open ground, and what it found when it got there, is where the story takes its strangest turn yet. Leave the ocean for a moment and look at the land above it, because for almost the entire story so far, the land has been bare and brown and silent, scoured by wind and rain, with nothing growing on it. Life had been busy in the water for hundreds of millions of years, building eyes and shells and predators and whole food chains, while the continents sat empty above them. Every living thing on the planet was still trapped in the sea. An entire world of open space and untouched ground sat above a crowded ocean with nothing living in it. Something had to make the first move out of the water into air that no animal had ever breathed, and onto rock that had never held a footprint. The leap seems almost impossible from where we sit, since a body built for water faces drying out, collapsing under its own weight and finding nothing familiar to eat the moment it hauls itself ashore. Yet life did make that crossing, and once it had, the land would never be empty again. So who went first onto that bare ground, and what did the land look like in the first moments anything living tried to cross it? But the land that the first organisms crawled onto was not welcoming. There was no soil in the modern sense, only crumbled rock and mineral dust, with none of the organic material that makes ground fertile. And no root systems had yet broken stone into the finer particles that plants would eventually need. The air was breathable, but only just, with oxygen levels still lower than they are today, and no shade anywhere to reduce the exposure to solar radiation on open ground. The first moss clung to the damp edges of water because it had no choice. Move even a few meters from the moisture and it would dry out and die, since it had no internal plumbing to carry water to its own cells. Every step away from the water's edge was a step toward conditions the organism had no tools to survive in, and the animals that followed the plants ashore faced the same problem in heavier bodies. A creature built for buoyancy in water collapses under its own weight on land unless its skeleton and musculature can compensate, and early arthropod bodies were not designed for the sustained effort of moving against gravity across dry ground. The first animals to come ashore did so for short periods and retreated. The land tolerated them without yet being able to support them. The answer to how life escaped the water turns out to be that plants went first, and everything else followed the oxygen they made. Algae crept onto damp ground and became the first moss, clinging to the edges of water because it had no roots to draw moisture inland. Over time, those early plants evolved real stems and vascular tissue, structures that let them carry and hold their own water, and that single upgrade let green life push away from the shoreline and spread across open land for the first time. As the plants spread, they exhaled oxygen, and the first animals to follow them out were the arthropods, millipedes, centipedes, and early scorpions that crawled from the water into a world with food and almost no competition waiting for them. By the Carboniferous, the consequences had grown literally enormous. Oxygen in the air climbed from around 15% toward 30%, and in that thick, rich atmosphere, the arthropods swelled to sizes that would be impossible today. Arthropleura, a millipede, stretched to roughly 2.5 meters and 50 kilograms, a creature the length of a car. And despite looking like a nightmare, it was a harmless vegetarian that fed on dead plant matter. Above it flew Meganeura, among the largest flying insects that ever lived, with a wingspan near 75 centimeters, close to a crow, a light and fast predator that hunted in short, darting bursts. Land had been claimed, and the creatures claiming it were larger than anything that crawls or flies today, though nothing yet explained how bodies built on the plan of an insect could possibly reach that size. Knowing that something crossed onto land is not the same as knowing how the land produced creatures the size of cars. The moss and the millipedes and the giant dragonflies did not appear simply because the ground was available. Something specific about the world during that period made enormous size not just possible, but ordinary. And the reason belongs to a particular moment in the planet's history that has never repeated. Stay with those giants a little longer, because their size is not a detail you should let slide past. A millipede long enough to fill a car. A flying insect with wings spanning the length of your arm. These were not rare freaks at the far edge of their kind. They were ordinary residents of the Carboniferous world, and creatures like them turned up across the swamps and forests of the age. Anything that size today would be impossible. Step on a beetle now, and it is the size of a coin, and the largest insects alive in the modern world could rest in your palm with room to spare. The forests crawled and buzzed with monsters, and the seas, as we will see, were hiding hunters every bit as oversized. There has to be a reason a planet can grow insects to those proportions in one age, and cap them at a few inches in the next. So what was so different about the world back then, and why has nothing on land or in the water ever grown that big in the same way since? But the oxygen surplus that made the giants possible was not a stable feature of the planet. It was a product of a specific arrangement of forests, atmosphere, and geography that had never existed before, and would never exist again in quite the same form. The Carboniferous coal swamps were producing oxygen at rates the planet's chemistry could not sustain indefinitely. And the same forests driving those levels up were already changing the soil and the water chemistry around them in ways that would eventually undermine the conditions they depended on. The oxygen peak was real, but it had a ceiling, and that ceiling was being approached at exactly the moment the giants were reaching their maximum size. In the seas, the Eurypterids faced the same precariousness from a different angle. Their bodies required specific water temperatures and dissolved oxygen concentrations to maintain the metabolic rates that kept something 3 meters long alive and moving. And those concentrations were already beginning to fluctuate as the climate above the ocean shifted. The giants on land and the giants in the water were both expressions of a surplus that the planet was quietly drawing down, and neither had any biological mechanism for registering that the drawdown had begun. So the question hanging over those monsters finally has its answer, and it comes down to 2 things working together. The arthropods grew that large because the air was thick with oxygen, and their bodies breathed through tiny holes rather than lungs, which means more oxygen in the air directly allowed bigger bodies to stay supplied all the way through. The second reason is just as important. The vertebrates that would later compete with them and eat them were still rare and small. So the giant arthropods grew into a world that had not yet built anything capable of stopping them. The seas told the same story through a different cast. There, the dominant hunters were the Eurypterids, the sea scorpions, though they were never true scorpions at all, but a separate branch of evolution that simply happened to look the part. The largest of them, Jacalopterus, reached somewhere between 2.5 and nearly 3 meters, ranking among the biggest arthropods the planet has ever produced. And it hunted fish and smaller arthropods as an agile, fast-turning predator. Some could even drag themselves onto land for short spells, keeping their gills wet enough to function out of water. Every one of these giants, on land and in the water, depended on the same thing: an atmosphere stuffed with oxygen and a world too young to have built anything that could push back. But that thick air and that empty stage were both features of a particular moment, and the continents underneath all of it were already grinding toward an arrangement that would strip both away. A world built on a chemical surplus is not a stable world. The oxygen levels that turned ordinary insects into monsters and filled the shallow seas with 3-meter hunters were already moving toward a ceiling. And beneath the swamps where the giants lived, the ground itself was rearranging into a shape that would take everything the surplus had built and quietly dismantle it. Worlds like that, full of giants and thick with breathable air, can feel permanent while you are standing in them. This one was not. Beneath the swamps and forests where the great arthropods thrived, the ground itself was moving slowly over millions of years, carrying the scattered land masses toward one another on a collision that would eventually fuse nearly all the dry land on Earth into a single titanic continent. When that much land comes together, the consequences reach far past geography. Coastlines vanish. Weather patterns that had held for ages break down. The deep interior of such a continent sits impossibly far from any ocean, beyond the reach of the rains that had kept the old forests wet and growing and pumping out the oxygen those giants depended on. The world that had been kind to enormous insects was quietly assembling the exact conditions that would betray them. The giants were not killed by a predator or an asteroid, but by the shape of the planet rearranging itself underfoot. So why did the rise of one supercontinent doom the rulers of the age, and which creatures managed to survive a change that erased so many? But the formation of Pangaea did not kill the giant arthropods quickly. The drying was slow, spread across millions of years, and for much of that time the swamps and forests that remained still looked like functional habitats. Arthropleura appear in the rock right up until the coal swamps finally collapsed, which means these animals did not read the trend and adjust. They simply kept living in the shrinking pockets of the world that still suited them until those pockets closed. That is the particular cruelty of a gradual extinction. The environment looks adequate until suddenly it does not, and the animals, shaped by the old conditions, have no mechanism for anticipating the new ones. The oxygen was falling, but no Arthropleura measured it. The rains were retreating, but no Eurypterid tracked the trend across geological time. Each generation lived in a world that was only slightly worse than the one before it, within the margin of normal variation, until the margin itself ran out. And the amniotes moving into the spaces the giants left behind were not better fighters or faster runners. They were simply built around different constraints, and those constraints happened to match a drier, thinner-aired world in a way that the giants' constraints did not. The reason these giants had to go is written into the map itself. The drifting continents ground together into a single mass, Pangaea, ringed by one enormous ocean, Panthalassa, which covered more than half the planet's surface. That collision changed the weather everywhere. The lush, water-fed rainforests that had supplied all that oxygen broke apart and dried out because trees that once sat near water now found themselves stranded deep inland, far from any moisture, withering as the rains failed to reach them. As the forests thinned, the oxygen they produced fell with them. Temperatures dropped, and glaciers spread across the land. For the giant arthropods, built body and breath around a high oxygen world, this was a slow execution. Their entire way of living depended on air they were now losing. What carried a lineage through was a single piece of biology, the amniotic egg, a shell that sealed its own water inside, letting the young develop on dry ground without a pond to be laid in. That one adaptation split into two lineages here, one bending toward mammals and one toward reptiles. And it meant these animals no longer had to return to water to breed. In a world drying out from the inside, the creatures that survived were the ones that had stopped needing the water the giants could not live without. The collapse of the giant arthropods did not leave the land empty for long. Out of the drier, thinner world that Pangaea had made came a different kind of animal entirely, one with a backbone and 4 limbs and a body plan far closer to our own. And the first of them to truly dominate the Permian is a creature almost everyone alive today would mistake for something it absolutely was not. Out of that drier, harder world came the animals this whole journey has been building toward. The age of the giant insects was over, and the land now belonged to creatures with backbones, with 4 limbs underneath them, with bodies far closer to our own than to anything that had ruled before. This is the Permian, the long reign of the land animals that came before the dinosaurs and looked nothing like them. The world warmed as the period went on. The deserts widened, and across that aching landscape, one animal climbed to the top and stayed there. It is the one almost everyone has seen pictured, even if they have never known its name. A heavy-bodied predator with a tall fan of skin rising off its spine like a sail, stalking across the open ground. People who glimpse it in a book or a museum almost always file it under one heading without thinking twice. They assume it must be a dinosaur. That single assumption turns out to be wrong in a way that rewrites where this creature truly belongs. So what exactly was the sail-backed hunter of the Permian? And why does the answer connect it to us instead? But Dimetrodon's dominance rested on a Permian world that was still early in its transformation. The period opened cooler and wetter than it would become, which suited a predator of Dimetrodon's size, a large body in a warm but not extreme climate, with enough prey moving across the landscape to sustain it. As the Permian wore on and the interior of Pangaea dried and heated, the conditions that had made Dimetrodon's body plan so effective began to shift against it. The sail that helped regulate body temperature was an advantage in a world with moderate temperature swings, but as the climate pushed toward extremes, the same body that had been built to dominate began to carry the costs of its own bulk. Larger animals need more food and more water, and both were becoming harder to find across the increasingly arid interior of the supercontinent. Smaller, more efficient bodies were threading into niches that Dimetrodon could not reach, and the prey base that had sustained a 5-meter predator for 16 million years was thinning, and the ground left to hunt across was narrowing in ways its bulk could not follow. Its first true ruler is a creature most people would swear was a dinosaur. The Permian opened cool and then heated steadily, and across that warming land the synapsids took control, the lineage that leads toward mammals and eventually toward us. Their icon is Dimetrodon, and the most important fact about it is the one almost everyone gets wrong. It is not a dinosaur and never was. Sitting far closer on the family tree to every mammal alive today than to any dinosaur that would ever walk the earth. It grew up to around 5 meters and 225 kilograms, an apex predator carrying a mouth that mixed sharp slicing teeth with flatter grinding ones, letting it both kill and process prey that smaller hunters couldn't manage. The sail running down its spine, the feature everyone remembers, most likely worked to regulate its body temperature or to draw in mates, catching warmth and attention across the open ground. Dimetrodon held the top of its world for roughly 16 million years, a stretch so long it dwarfs the entire history of every upright human ancestor many times over. For all that time, nothing on land could touch it, and then it was gone, leaving the top of the food chain empty in a world that was only getting hotter, with new hunters already rising into the space it left behind, carrying teeth Dimetrodon never had. Dimetrodon's 16 million year run at the top was not the end of the Permian's predator story. What replaced it was built for a different kind of killing entirely, and moved through a world that was already quietly failing, a world where the numbers behind a functioning ecosystem were turning against every creature in it, visible or not, predator or prey. The sail-backed hunter held its ground for an almost unimaginable span. Then its time ran out, and the top of the food chain it left behind did not stay open for long. Into that space stepped a new kind of predator, and if the earlier ruler had been impressive, this one carried weapons the Permian had not seen before. The middle and late Permian belonged to hunters with long, curved fangs jutting from their jaws, weapons made for tearing into prey far larger than the small things their ancestors had chased. Around them moved a whole supporting cast of strange animals, some burrowing into the dirt, some grazing in slow-armored herds, a few already wearing the faint early features that would one day belong to mammals. From the outside, the late Permian looked like a thriving, functioning world, full of predators and prey going about the business of survival, exactly as they always had. But the setting around all that life had begun to change in ways no animal could see or smell or escape. The air was not what it had been. The heat was climbing past anything these creatures were built to endure, and the oxygen that every creature in it depended on had already begun to slide. So, what was happening to the world while its animals carried on as normal? And why did none of them sense the disaster already closing in? But the Gorgonopsians were hunting in a world whose foundations were cracking in ways that had nothing to do with predator-prey dynamics. The Permian had been warming for millions of years by the time the Gorgonopsians reached their peak, and the warming was not steady. It moved in pulses, each one pushing the baseline a little higher, each one stressing the vegetation that the herbivores needed and the water sources that every animal depended on. Scutosaurus and the other large herbivores were already walking farther for less, covering more ground to find the patchy vegetation left in an increasingly arid landscape, which meant their bodies were burning more energy for smaller returns. The predators that fed on those herbivores were following prey that was thinner and more widely scattered than it had been. The whole system was running on a shrinking margin, with each layer of the food chain slightly more stressed than it appeared from the outside. And underneath all of it, volcanic activity in what would later become parts of modern Asia was already releasing gases into the atmosphere in quantities that were slowly but measurably altering the chemistry of both the air and the ocean. The hunters that replaced Dimetrodon settled the question of what a Permian nightmare actually looked like. The Gorgonopsians ruled the Middle and Late Permian, and they carried saber-like canines up to 6 inches long, teeth built to shear straight through the skin of their prey, with the largest among them, Inostrancevia, reaching around 11 feet. Around these predators moved a strange supporting cast that fills in the rest of the world. There was Lystrosaurus, a burrowing herbivore, roughly 1 meter long that looked like a cross between a pig and a lizard, and the Cynodonts, small and rodent-like and already wearing whiskers, an early hint of the mammals to come. The Gorgonopsians fed on slow armored plant eaters like Scutosaurus, which lumbered across the land in search of scarce vegetation. Then the numbers behind this functioning world began to turn. The average temperature had pushed past 28 degrees Celsius, turning a once green world into something closer to an oven. The predators still hunted, and the herbivores still grazed, and the oxygen that kept all of it running had already slid toward 10% against the 21% we breathe today. Nothing alive could feel that number falling. The Gorgonopsian chased, the Scutosaurus fed, the whole system ran on as it always had, while the deadliest event in the planet's history was already underway, and not one creature in it knew the ground beneath them had begun to fail. A world running closer to its limit than anything alive in it could measure does not collapse on a schedule anything alive can read. The Gorgonopsians were still hunting, the herbivores were still grazing, and the Permian looked, from the outside, like a world carrying on. While deep in the rock beneath the supercontinent, something was building that would end not just this period, but nearly 300 million years of everything that had come before it. Everything this story has built toward, across billions of years, now comes to a single point, and it is not a triumph. The late Permian world was alive and crowded, and, on the surface, doing fine, with its saber-toothed hunters and its lumbering herbivores and its first hints of the mammal line, all sharing the warming land. Far beneath one corner of the supercontinent, in the rock, under what would much later become Siberia, an enormous reservoir of molten material was building toward release on a scale the planet had never witnessed before. and has never matched since. When it broke through, it would not be a single eruption, but a sustained outpouring, lasting far longer than any animal lifespan, an event large enough to poison the air, cook the climate, and reach into the oceans themselves. So how close did life on Earth come to ending completely? And what kind of world was left behind for the few survivors who somehow made it through? But the scale of what the Siberian eruptions released was not simply large by the standards of ordinary volcanic events. It was large by the standards of anything the planet's living systems had ever been asked to absorb. The carbon dioxide flooded into the atmosphere faster than the oceans, and the remaining vegetation could pull it back down, which meant the heat it trapped had nowhere to go but up. As ocean temperatures climbed, the water lost its ability to hold dissolved oxygen, and sea creatures that had survived every previous extinction event in the planet's history began suffocating in water that was chemically failing around them. On land, the heat and the acid rain produced by sulfur dioxide in the atmosphere stripped the last of the vegetation from exposed rock, and without plant, cover the soil eroded into rivers and washed into the sea, triggering the algae blooms that used up whatever oxygen the ocean still had left. Each failure cascaded into the next. The ocean dying made the land worse. The land failing made the ocean worse. The system did not reach a new equilibrium. It just kept contracting, each contraction removing more of what the surviving species depended on, until nothing was left. The end, when it came, was the worst thing that has ever happened to life on this planet. Massive volcanic eruptions tore open what is now Siberia, laying down lava beds half the size of the United States and pumping staggering volumes of carbon dioxide into the air. The heat soared. The oceans turned acidic and lost the oxygen that sea creatures needed to breathe, while on land, the wildfires spread and burned through whatever the drought had left standing. This was the Great Dying, the single most devastating mass extinction in Earth's history, and the figures are almost beyond belief. Somewhere between 90 and 96% of all marine species gone, and roughly 70 to 80% of land animals wiped away with them. Never before or since has so much living matter vanished from the planet in so short a span. The event didn't just close the Permian, it shut the door on the entire Paleozoic, a span of nearly 300 million years of evolution, predators and giants, all of it reduced to a thin layer of survivors. What was left was a world gone quiet in a way it had not been since before the Cambrian. Empty seas where the great hunters had patrolled, silent ground where the giants had fed, the air itself thinned to something that could barely keep the survivors breathing, and almost nothing left alive on a planet that had just killed nearly everything it ever made. If there's a period of prehistory you'd like to hear next, drop it in the comments. This story has a long way still to go.